Yeah. Hello, good morning. I hope everyone is ready to start. Yesterday we had the kickoff lecture on superstrings, yesterday all you saw was bosonic strings, and it's the same today. One of the highlights was the Polyakov action, trying to describe how strings propagate in space-time. So the arena of most of what we will be doing throughout this course is the string worldsheet, this two-dimensional surface which tracks the world lines of every point on a string. I mean, both for closed strings and for open strings, there's a sensible notion of worldsheet. It has boundaries in case of open strings and accordingly no boundaries in case of closed strings. And we will have a systematic discussion of open strings tomorrow, so you can assume the strings I'll be talking about today to be closed. Yeah, and this two-dimensional worldsheet will be embedded in Minkowski spacetime. I just use capital D to refer to a generic number of spacetime dimensions. And the way how this embedding works is governed by that Polyakov action, say by solving the equations of motion when you're after the classical perspective. There are two fields now in the Polyakov action. This H alpha beta is a worldsheet metric, which is here taken to be in principle independent. But at the same time, there is no dynamics to it because there is very rich symmetry to this Polyakov action. Actually, as many symmetry degrees of freedom as the metric has components. I mean, the metric, you can view it as a symmetric 2x2 matrix, which means there are 3 independent entries. But for each of them, we have some kind of symmetry mechanism to fix it. So first of all, there are the diffeomorphisms that you can change your mind about the coordinates. So you can do diffeomorphisms in 2 dimensions, going from sigma alpha to some twiddled version, which may have any functional dependence on the old coordinates. And there was furthermore a symmetry under Weil transformations, where you rescale the metric and do nothing at all to x. And let me stress, this Weil transformation is not meant to be a diffeomorphism, but an independent type of symmetry. It's really tied to being in 2 dimensions that this Weil invariants work, because otherwise the determinant would not have the right scaling to be compensated by the Weil transformation of the inverse metric over there. We were yesterday discussing some particularly good choices how to use the symmetry. I think I will also speak of gauge. I mean, you can view this as a gauge symmetry. Both diffeomorphisms and Weil are local symmetries. So you can, so to say, gauge the metric into your favorite form, at least locally. So a very, very convenient form already is to demand that as a 2x2 matrix, the metric should be proportional to the Minkowski metric. But now this is Minkowski on the worldsheet, diagonal -1, +1. And it's even enough to be proportional to eta alpha beta with a scalar factor omega square that, well, can depend on sigma in any way it wishes to. It nevertheless gives us a super nice form of the action. I mean, just kinetic term for free scalars. And accordingly, the equations of motion for x in conformal gauge are as simple as that, a wave equation in 2 dimensions. We were looking at a solution to this wave equation compatible with the periodicity in sigma required for closed strings. You saw some Fourier expansion with modes alpha n. And I guess in most string theory courses, the next step would be to go to the quantum level and promote the Fourier coefficients alpha n to operators. I won't do that straight away. They will enter through the back door in a later stage of today's lecture, but I will now depart from many storylines in string theory courses and instead give a focused discussion of conformal field theory. This will, at the beginning, require a bit of work or require your attention to absorb a bit of formalism, but you have my promise that this will pay off, both within string theory and also in other areas of physics, including statistical systems and condensed matter. Yeah, and in this conformal field theory framework, a key role is played by the energy-momentum tensor. So yesterday I was defining the energy-momentum tensor as the variation of the action with respect to the metric. And I guess this is a pretty general definition for energy-momentum tensors, which you also may have seen in the GR course. But here it's the energy-momentum tensor for the worldsheet. So as usual, it has these indices alpha, beta running from 0 to 1. So please don't confuse it with energy-momentum tensor in space-time. And well, yesterday you mostly saw it as a name for the equation of motion with respect to h. I mean, even if we can gauge away the dynamical degrees of freedom in h, there is still some trace of it through its equation of motion. I mean, you must know about its equation of motion, and you can go to conformal gauge after determining the variation of the action. So first, compute the energy-momentum tensor at generic h, and then go into your favorite gauge. So that expression has to vanish as consequence of the equations of motion for h, and this for sure imposes various constraints on the Fourier coefficients that you saw in the classical mode expansion. And one of the key challenges in quantizing bosonic strings is to deal with the constraints. I mean, if it wasn't for constraints, there is a easygoing recipe, canonical quantization, compute Poisson brackets, promote to operators. That's all a smooth sail until you face the moment of imposing the constraints in the quantum theory. And one of the advantages of the conformal field theory setting is to settle all of these difficulties, to find a natural way how to implement the constraints. Okay, this is the theme for today. On the one hand, this equips you with some general toolkit on two-dimensional conformal field theory. And on the other hand, I will stay in close touch with a specific example of Polyakov action, or I will just refer to these x mu coordinates as the free boson. And what this buys us is we will get an infinite dimensional symmetry, which we can bring on our side. I mean, you already know it from the good old Kepler problem that having a finite number of symmetries is great. And needless to say, whenever there is a perspective to get an infinity of symmetries or conserved charges, then this is the holy grail for any theoretical physicist. So that's something we will develop and use. And we will furthermore arrange coordinates to be complex, such that we can borrow various theorems from complex analysis. So don't worry if you don't have everything on your fingertips all the way to the Liouville theorem. It's just a small number of theorems on meromorphic functions that I'm going to use. Easy to state, but at the same time, really powerful. Yeah, so this is the motivation and plan. Are there any general questions about the flow of logic before I flesh out more details? Okay, then let's see how we get a sensible infinite dimensional symmetry from the Polyakov action. Okay, so maybe some of you were rolling their eyes. Of course, there is something infinite dimensional if there are diffeomorphisms in Weyl, but actually I have in mind to look at a residual gauge invariance that even after diff cross Weyl, there will be an infinite dimensional symmetry. So as I was already reviewing on the other board, the first action to be taken when staring at Polyakov action and its beautiful symmetries is to gauge fix the metric. And let me here go a step further than I did on the other board. let's here use the complete power of both diffeomorphisms and Weil. I mean, up to here it's diffeomorphisms, but then as a second step you can use Weil invariance to kill the scalar factor or to send capital omega to 1. So let's look at this gauge choice where at least locally the worldsheet metric is trivialized to the Minkowski one. Now the big question is, does this completely gauge fix all of diffeomorphisms in Weil invariance? I mean, it seems like the counting of degrees of freedom matches 3 jokers for 3 components. However, this is not quite the end of the rope. And this is the starting point, which leads us into conformal field theory. There is still a residual gauge freedom. Namely, there is a distinguished class of diffeomorphisms which you can undo using a Weil transformation. So let's review how the metric transforms under such a diffeomorphism. I gave you this transformation law that you know from GR for a contravariant 2 tensor. Both of these indices get contracted with a Jacobian. Whoops. And suppose you fine-tune the diffeomorphism sigma twiddle such that this gives a multiple of the previous metric, scale factor times the old h. Then this can be undone using a Weil transformation. Of course, this is a highly specialized choice of diffeomorphisms. If you cook up a random choice of sigma twiddle, it will of course fail to satisfy this and completely distort the matrix structure of H. So this is really about privileged subclass. So just to be clear on what I mean, we start with this gauge choice, where naively it seems like we are done with diff cross Weil. But here I'm pointing out the loophole. No, we are not done with diff cross Weil. Let's give a nickname CT to this transformation here. So then we can start from Minkowski. We do one of these special diffeomorphisms in equation CT, which brings us to this multiple. And then you do a Weil transformation, a compensating one. And then you are back at this. So this combination, privileged diffeomorphism followed by a Weil transformation, this is a residual gauge freedom of Polyakov action with this choice of worldsheet metric. Yeah, and as this shorthand already suggests, these diffeomorphisms are known as conformal transformations. Those diffeomorphisms that only rescale the metric. And okay, this definition holds in general numbers of space-time dimensions. I mean, clearly, this equation by itself does not very much refer to the number of space-time dimensions. Okay, these are conformal transformations. And yeah, as I'm saying, this exercise of classifying conformal transformations can be done in any number of space-time dimensions. So suppose you do that in 3 or more dimensions. Then it's easy to unravel the group structure of these conformal transformations and doing an exact counting. And clearly, the composition of 2 conformal transformations is again a conformal transformation. That's why I'm shamelessly speaking of a group here. And yeah, you find the number of generators in some generic number of space-time dimensions is given like that. It's a simple quadratic function of d, the number of dimensions. And you can already smell that this is counting antisymmetric matrices. And in fact, if you look at the commutator relations among those conformal generators, you find that it is isomorphic to a variant of Lorentz group, but with a more funky signature. Okay. I won't spell them out unless you really ask me to in the question and answer session here, but this is just to say that yes, conformal transformations exist in general number of space-time dimensions, and there are finitely many of them, at least if d is larger than 2. Now, lucky us that we are in d equal to, as dictated by the string worldsheet, because there something really beautiful happens. In d exactly equal to, all of a sudden, the conformal group enhances to become infinite dimensional. Oops. How is that coming about? So what kind of miracle occurs in 2 dimensions but not in higher dimensions? An easy way of seeing what's special here is to again go for light cone coordinates, which we already used yesterday to clean up classical solutions. So once more, sorry? Oh, sure. Suppose you do a very special diffeomorphism which brings the old metric h into this form, like a scalar prefactor times the old one. So now let's say I'm done with the diffeomorphism, and now I go back to my checklist of symmetries, and I find Weil transformation, which by definition rescales the metric and leaves x inert. About x I'm not caring here, I'm only caring about the metric. And now I do a Weil transformation, which by definition multiplies the metric by my favorite scale factor. And the reason that I picked this exponent here, my variable choice in the Weil transformation was omega square is the multiplication factor. Multiply this by omega square and all the prefactors are gone. So you can roll back to the previous metric at omega square equal 1, so to say. You can get rid of the scalar factor. Does that make sense? Good. All right. I think I was about to show you a nice property of the metric in 2 dimensions. Here I'm writing the metric in terms of the invariant line element. And in light cone coordinates, this factorizes. So with a factorized metric, it's even easier to study under which condition does it pick up a multiplication factor like omega square. So what can you do with it to rescale? This one simply rescales if you do a 1-variable diffeomorphism. Suppose you change your mind what sigma plus means. This I would call a 1-variable diffeomorphism. Send sigma plus to some arbitrary function of sigma plus only, but not of sigma minus. Let me emphasize it in that almost ridiculous manner. Then, well, you don't touch the d sigma minus, but by the chain rule, you get a Jacobian factor for the change of variables for sigma plus. And you can independently play that game for sigma minus. So, in fact, we should look at pairs of 1-variable diffeomorphisms, where you do this transformation to sigma plus, and then independently, you can send sigma minus to yet another arbitrary function g of sigma minus. Doesn't have to be the same function as the f over there. And once more, it's essential that this is a function of 1 variable. Yeah, and the reason I keep on dwelling on infinite dimensional is just try accounting. How many of such functions are there? For sure, there is infinities of choices for such f and g. So in a certain sense, it's even twice times infinitely many, because you can dial f and g independently. So the good news is that there are infinitely many such moves, all of which are residual gauge freedom for the Polyakov action with Minkowski metric. Okay, now how did this magic work? I mean, some of you may have expected 5 minutes ago that there is no more gauge invariance, because we did a degree of freedom count before. But recall that initially we did diffeomorphisms in 2 variables. And the residual gauge freedom we are finding here is a 1-variable diffeomorphism. So for sure, this is extremely constraining. There are considerably less diffeos in 1 variables than there were initially in 2 variables. Even though it's still infinitely many, it's nevertheless a rather modest portion in comparison to the original diffeomorphism freedom. I dare to say a set of measure 0. So this is how we are not violating any earlier insight by identifying an infinite dimensional residual gauge invariance. Set of measure 0 in the set of all possible 2-variable diffeomorphisms considered before. Okay, light cone coordinates are pretty good to illustrate this factorization property of the metric and to expose that all of a sudden your conformal group enhances to an infinite dimensional one spanned by all choices of 1-variable diffeomorphisms f and g. And now let's go for the other thing on the bucket list. Complex analysis was promised in the outline to this lecture. And as a 0th order step into this direction, let's introduce complex coordinates. And in order to do that, we need the infamous Wick rotation. We pass to an Euclidean version of the worldsheet time. So maybe some of you have seen this in quantum field theory, that for many properties, in particular for thermal quantum field theories, it's beneficial to leave the real slice for the time coordinate. And instead of the time, you look at minus I times time. Okay, and here I hope the notation is not too confusing. We were previously working with the proper time coordinate tau, which was probably assumed to be real, and we now make the heretic move of Wick rotating it to be minus I times a real variable t. So please don't confuse this t with 0th direction in Minkowski spacetime. I really mean just yet another worldsheet variable. Okay, so let's do this Wick rotation. And, well, I can mumble the same words that your QFT lecturer was mumbling back then. Such a Wick rotation is all right, as long as you don't cross over poles in the complex time plane. And it's admittedly not manifest from things I'm doing right now, but also on the worldsheet. You will, at the end of the day, get away doing that. In a certain sense, the change of integration contour to do that is not crossing any tricky points. So I hope you're ready to believe me this for the moment. And accepting this Wick rotation, we can now use the following complex variables to parameterize the worldsheet. There's yet another factor of I that I'm putting into the light cone variables. And since tau was Wick rotated, we have the same real part to the rescaled version of the light cone coordinates. So this is a convenient coordinate system to start our excursion into complex analysis. And needless to say that the metric still factorizes. It looks like that in the z and z bar coordinates. Yeah, and now I can restate what the conformal transformations in 2 dimensions are, written in these complex coordinates. So in the sigma plus, sigma minus coordinates, the big deal about conformal transformations was that they don't mix between plus and minus. And well, in complex analysis, if you demand a complex function to not mix z and z bar, this is another way of saying it's meromorphic. So this f from over there is about meromorphic functions operating on z, and then that g from the other blackboard, this is about antimeromorphic functions operating on z bar. Okay, imposing a transformation to be a conformal one just amounts to imposing meromorphicity. So it's in this framework that I want to study conformal transformations in the rest of the course. So as was stated before, the benefit of these conformal transformations, I mean meromorphic F, antimeromorphic G, is that the metric simply gets rescaled under those. Yeah, so this is the infinite dimensional conformal group in 2 dimensions. And in order to further study its properties, the properties of the group, let's switch into the algebra. Probably the same logic that you saw in particle physics and QFT courses. Whenever a symmetry study is getting more intense, it's nice to have a vector space structure, and then it's easier to play with the algebra rather than with the group itself. Yeah, exactly same logic here. We now go for the conformal algebra. Like infinitesimal conformal transformations whose exponentiation gives back the large conformal transformations. And I want to give you an infinite dimensional basis for possible meromorphic and antimeromorphic maps. So let's organize this infinity. I hope it's not confusing. This is counting infinitely many of them. And here infinitesimal means that they are assumed to be small in the subsequent. So how can I make a map small? Let's look at maps that are very close to the identity. And they only differ by some small epsilon. And here is the infinity of options. For each integer exponent, z to the whatever that I choose to add, I get a meromorphic map. Remember, meromorphic means holomorphic, but may have poles. So don't get scared in case n is negative or -2 and smaller. Poles are allowed in meromorphic functions, and poles don't crash this property of the conformal transformation. Yeah, so this is one possible basis choice for the algebra. Or, okay, to be more precise, I still need to convert this map into an operator. Suppose I do this map inside a function of z. How do I tell the function that this map is happening? There's a differential operator induced by that. So the associated generator is, so doing a translation means you differentiate, and then you look at by what you translate. We are translating by z to the power n plus 1. So this is the differential operator that implements this transformation. And if you're wondering about the minus sign, this is that confusing distinction between active and passive transformation. Don't ask me to spell that out in real time. Yeah, so this differential operator here takes care of all these meromorphic maps. And of course, there is a completely analogous construction when z is renamed into z bar. So for the anti-meromorphic ones, you have those generators L bar. Yeah, and the key property in, well, any Lie algebra is the collection of commutators. So what kind of commutators do we get from these concrete differential operators? We get, well, two decoupled towers. Maybe the most important information is that z doesn't talk to z bar, which means that all the unbarred L's commute with the barred L's. So this is a huge collection of trivial commutators. But what are the non-zero ones? Those are also known under the name Witt algebra, and the brackets go like Lm, Ln. Well, this is not easy to verify. And on the right-hand side is L with the sum of these subscripts. Yeah, so a similar type of algebra, known as the Virasoro algebra, will be introduced later today. You can view this as a kind of preview of the algebra that will govern the energy momentum tensor modes that will ultimately need to be imposed as a constraint. So that's a warm-up, and its central extension will be delivered in the next hours. But before going there, let me point out that there is a particularly nice subalgebra. Namely, as I was saying, there may or may not be a pole in here, and if we are conservative and want to make sure there's no pole, then the first idea is to restrict n to be -1 or larger. Yeah, -1 or larger means no pole at the origin. But conformal transformations, they most naturally live on the Riemann sphere, where we not only allow for complex numbers, but we even take the point at infinity series. So we just talked about pole at the origin, but for the Riemann sphere, we should also ask about pole at infinity. And admittedly, that's a bit tricky, how to assess the behavior at infinity. Easiest way to get it is to change variables, z equal 1 over w. And what used to be point at infinity in z becomes the origin in w, and you do the same kind of assessment. This operator in the w variable, does it have a pole at the origin in w? So with this you get another bound, or you rule out another infinity of generators. And what you find, if you want to have no pole whatsoever, neither at the origin nor at infinity, then there are only 6 generators to do the job. So only those 6 generators are globally defined on the Riemann sphere. I mean, I'm not saying that the others are boring or unacceptable. It's just that there is something more to say about this subalgebra. And if you want to give them a name, this turns out to be the Lie algebra of SL to C. It's 6-dimensional, so the counting already fits to SL to C. And I can also give you the associated group when exponentiating this privileged subalgebra. Exponentiating gives you the so-called Möbius transformation. Like go for all the 6 choices, then, or maybe for simplicity, look at the meromorphic ones at the beginning, and the exponentiated version of these differential operators here, they take you into such a Möbius transformation. And the connection to SL2C comes about from the fact that, well, these parameters A, B, C, D, they can readily be rescaled. I mean, a rescaling just drops out from the fraction. So I can, without loss of generality, impose that written as a matrix, they should better have unit determinant. If it was not the case, you could just rescale all of A, B, C, D to enforce a unit determinant. So it is this very concrete realization of SL2C which is sitting in that subalgebra here. And that will, for instance, become very important when we discuss string tree-level amplitudes. But there's another neat aspect of that I want to highlight. I gave you the counting in D dimensions, claiming that there is that number of conformal generators in general D, and there is a shadow in D equal 2 of that statement. If you send D equal 2, you would naively expect 6. And indeed, that formula counts exactly those 6 here. So this is, so to say, the remnant of the conformal generators you can write down in a dimension agnostic way. So if I had more time, I would elaborate on those being translations, Lorentz transformations, dilatations, and special conformal ones. And whatever you can do in a dimension agnostic way, it specializes correctly to those 6 here. So that is inherited from the dimension agnostic counting, since this one specializes to 6 upon setting D equal 2. Yeah. So it is those conformal generators which have poles at either the origin or infinity, which have not been counted by the naive formula. Or it's thanks to these extra generators with poles that we have an enhancement to an infinite dimensional symmetry.
Oh, is the group SO22 isomorphic to SO2C?
Let's see. Okay, so here SO2, 2. Locally for sure, SO2, 2, I mean it works like SO4 up to signature, and SO4 is known to factorize into SU2 cross SU2, and then combining these two factors of SU2 to a complexified one, then we arrive at the SO2C. Yeah, viewing this as a complexified SU2. Okay, right. There may be some discrete identification. I'm sorry, I won't be able to answer that on top of my head. Maybe you can help me in the break understand. Okay, yeah, so the upshot is, here we looked at the residual gauge invariance of Polyakov action in Minkowski metric, and that has an infinite dimensional symmetry arising at residual, as residual gauge invariance. So it's the infinite dimensional conformal symmetry in 2 dimensions. From residual gauge invariance. And once more, the word gauge is borrowed from the fact that the underlying transformations are local. I mean, both Diffeos and Weil transformations were free to depend on the worldsheet coordinate sigma. This is residual gauge invariance of Polyakov action at the simplest choice for the metric you could imagine. Yeah, so this was a set of entry remarks into conformal symmetry. And now I want to go a little bit deeper into that and tell you a bit about the Noether currents of the conformal algebra. I'm sorry? Global? Well, I would say a local one for the world sheet. Yeah, these F and G are allowed to be Z-dependent. Oh, okay, this is what made you nervous. Okay, I see. Let me see. Okay, ask me again when we are at this expression. Now, I'm a bit confused myself. Yes, global, local. I see why you are asking this, yes. All right, what are the conserved currents? Well, let's do this quite generally, of general two-dimensional CFTs, even those that we don't meet on the world sheet. Okay, to do a couple of modest warm-ups, consider some general diffeomorphism now in the infinitesimal version. I mean, I gave you the large version of diffeomorphisms when the metric transforms with Jacobians, but now suppose the diffeomorphism is very close to the identity, that sigma twiddle is almost sigma up to a small parameter eta alpha. Then if we work to first order in eta, I mean if we work infinitesimally, then this formula for the metric changes like that. And let's see how this induces a change in the action. And I'm just assuming, let's say we are in a two-dimensional CFT, which can be described by an action functional, but it doesn't have to be the Polyakov action. So a general action, possibly distinct from the Polyakov one, will vary as follows. So this is the same type of field variation as if I'm about to compute equations of motion. So it's something like an infinite dimensional chain rule that we are using here. So whenever we check how the action varies, we take the field variations for all possible points and multiply by these corresponding variations at that point sigma. And now, for both of these ingredients, we have seen expressions before. The variation of a general metric is essentially the energy momentum tensor. So with the normalization conditions of the previous lecture, this is almost the energy momentum tensor up to this determinant factor. And then for the diffeomorphism variation, we were saying, let's plug in the infinitesimal transformation right here. So then the energy momentum tensor is contracting this outer derivative, partial alpha of eta beta. Now this works for arbitrary diffeomorphisms, but now what's nice about conformal transformations? If you now specialize that thing to a conformal transformation, then the energy momentum tensor is getting traced. Let me elaborate. So if this was a particular diffeomorphism, namely a conformal transformation, then this outer derivative here will be proportional to the metric, I mean, as a 2 by 2 matrix, but of course there can be a scaling factor. I was close to writing capital omega square in my notes, but now that everything is infinitesimal, I want to make sure that I'm using a lowercase version. Sorry about the multitude of letters. Okay, so let's revisit that calculation over here. How does the action change if it's a conformal transformation and not a random diffeomorphism? So then it's proportional to, well, the determinant factor stays the same, but now, as I was announcing, the energy momentum tensor is now getting traced. So all the indices alpha beta are now hanging on the metric up to a scale factor. Okay, and if this is to be a symmetry, if we demand this to be 0, leave the action invariant, then it means that I will have to set the integrand to 0. Okay, let me say things cleanly. In conformally invariant theories, you want, by definition, that a conformal transformation leaves everything invariant, including the action. So at the very least, that integral has to vanish. However, this has to work for arbitrary choices of omega square. So for any test function here, that integral has to vanish. So I can extract a stronger statement that the integrand has to vanish, namely the piece of the integrand different from omega. So this is now a general property of conformal field theories. I didn't even use two-dimensionality. In general conformal field theory, the energy momentum tensor is traceless. And indeed, we were seeing that happening yesterday when we looked at the particular theory, namely Polyakov action in 2 dimensions. We had this energy momentum tensor in front of us, and we were pondering about how many constraints it entails. And yeah, we saw that it's traceless by inspection. And here, all the loose ends are tied together. The Polyakov action, even in gauge-fixed metric, gives you a conformal field theory. And as such, it must benefit from that tracelessness statement. So it was bound to happen that our energy momentum tensor from the Polyakov action is traceless. Okay, so no surprise for what we saw yesterday, but giving a more general perspective that this is also true in higher dimensional CFTs. Okay, and I felt that we should first settle the degrees of freedom in the energy momentum tensor before we can talk about the Noether currents and before we can settle the global versus local question. Okay, so let's gear towards Noether currents, and for the moment, let me just impose translation invariance. Let's for a moment refrain from imposing conformal symmetry and see how the general mechanism works. In a general translationally invariant theory, we have that the energy momentum tensor is conserved in the sense of that this tensor divergence vanishes. Oh yeah, and let's furthermore make our life simple and take a Minkowski background. So with these prerequisites, metric going to Minkowski and imposing translation invariance, what can we say about the above variation? So I'm doing this, of course, after the variation above there. So then that variation of the action allows me to pull out the partial alpha derivative. I mean, before committing to translation invariance, I had the partial alpha only acting on the eta beta. But all you need is translation invariance, and then you can pull it out globally. And now this is in the perfect form to read off Noether currents, namely whenever a variation takes a total derivative form, then the object whose total derivative you take is the Noether current. So in this way, we can read off the conserved Noether current of the infinitesimal diffeomorphism. So that Noether current associated with this diffeomorphism eta is essentially the energy momentum tensor contracting this eta vector. Okay, so in an attempt to answer your question, so yeah, we are using locality. I mean, we are using that eta depends on sigma. And now I guess what is unusual here, we are not planning to unpromote eta. We are not planning to make eta independent on the coordinate. Okay, so this is the general story for generic diffeomorphisms. And let's now check what simplifies in conformal theories. And this can most neatly be done in complex coordinates. So let's once more take this cleanly factorizing metric in conformal coordinates. Then I evaluate this contraction over beta in complex coordinates. As I was warning you yesterday, it's already tricky in light cone, but also tricky in complex coordinates that z's turn to z bars as you raise and lower indices. So I very much hope that this is not a typo. The index of eta is anti-correlated with the upper index of t that it contracts. So this is pitfall number 1. And pitfall number 2 is, if we now want to look at the downstairs components of t, then the upstairs z's become downstairs z bars. So admittedly, this is all a bit confusing when doing it for the first time, but let me assure that this is some algebra that you will all have under control if you sit down with it for 10 minutes or so. Okay, so this is, oh, I think here is a first mistake, like that, right? Yeah, now it feels a bit better. Right, otherwise the simplification in the conformal case doesn't work. So, as I said, up to and including here, I'm not assuming conformal invariance. Let's now look at the conformal case. So first of all, as we just saw, in conformal theories, energy momentum tensor is traceless. And the trace in light cone or in ZZ bar becomes the off-diagonal. Okay, so the virtue of conformal symmetry is that that term here goes away. So that simplifies that study of the current a little bit. And then the next thing to note, the conservation law of the current gives rise to meromorphicity, or is tantamount to meromorphicity. And in order to see the respective meromorphicity properties, I first use the conservation law of the energy momentum tensor. Okay, so this is always part of conformal symmetry. And also it was a prerequisite for the entire board here. So conformal symmetry, together with this conservation law of the energy momentum tensor, it means that the non-vanishing components of T are either meromorphic or anti-meromorphic. I mean, if it wasn't for conformal symmetry, then this conservation law would always have two terms. You're contracting over alpha, you get two terms. But one of them is the plus-minus component, which vanishes by tracelessness. So in conformal field theories, the conservation law of the energy momentum tensor simplifies further like such. Okay, there's a good moment for a break in 3 minutes, almost there. Yeah, so what I just wrote here, it simply implies that the non-zero components of T, the two survivors, are either meromorphic or anti-meromorphic respectively. And let's give them nicknames. I mean, as you see, it's pretty annoying to write all these ZZ downstairs or Z bar downstairs. So let's use this shorthand. T without any specifier if I mean the ZZ component, and T bar without any specifier if I mean the Z bar component. So this is doing two things at the same time. I'm introducing the shorthand, T without subscript, what it means, and I'm stressing that we just found by this conservation law that you have one anti-meromorphic component and one meromorphic one. So this is the only type of energy momentum components that will enter these Noether currents. Yeah, and now to finish that off, Noether currents. Now, let's not only take the theory to be conformal, but let's furthermore take that diffeomorphism eta to be conformal. So, imposing eta to be a conformal transformation means that its Z entry is meromorphic and its Z bar entry is anti-meromorphic. And again, I'm doing both a meromorphicity statement and a definition at the same time. You saw already here how the notation lightens up if we stop tracking the subscripts. If we write eta without anything, then it refers to the Z component of this conformal transformation. And likewise, an eta bar refers to the Z bar component. And since conformal transformations are those meromorphic and anti-meromorphic maps, we have an eta of Z as a meromorphic map, and likewise eta bar is anti-meromorphic. So long story short, we take away from all of this that the Noether current for conformal transformations has a meromorphic and an anti-meromorphic component. Oops. So I think this is what I would have denoted by J upper Z. So this component of the Noether current is a product of T and eta, T being the ZZ component of the energy momentum tensor, and eta being one of the two components of the diffeomorphism, and both are meromorphic. Okay, I see that I do the assignment in the wrong way. Yeah, there is one meromorphic component to the Noether current, and one anti-meromorphic component. So in the second case, it's a copy-paste, putting bars everywhere. Yeah. So all this to say, in conformal field theories, there is a lot of butchering on the Z and Z bar components of various tensors and in the Z and Z bar dependence. So for the energy momentum tensor, there are only two surviving components, one meromorphic, one anti-meromorphic. And exactly the same statements go through for that diffeomorphism eta, which is specialized to be a conformal transformation. One purely meromorphic gadget, one purely anti-meromorphic gadget. And with those, we will have a lot of follow-up discussions after the break. Okay, everybody back from coffee? Let's go on. The next section is about cylinder versus plane and contour integrals. What will this be about? Well, the first half of this section is to rethink the optimal coordinate system for the string worldsheet, where optimal is, of course, in the eye of the beholder. I will do yet another transformation to the combination of tau and sigma, which allows us to automatize the periodic direction of the closed string. I mean, we were every now and then imposing that the spatial coordinate sigma for the closed string worldsheet is periodic, going from sigma to plus 2 pi. It's annoying to track that all the time, so part of the benefits of going to the plane is that this will be automatic. Yet another virtue of going to the plane is that infinite past compactifies to a point. And if you interpret the plane as a Riemann sphere, then even infinite future is sitting on a point. I mean, infinite past, infinite future will be very important when we discuss asymptotic states and scattering amplitudes. And it's more comforting with all the asymptotic states being mapped to just a point, say the origin or the point at infinity. So these are the global motivations why I will take you from the cylinder to the plane. And at a technical level, once we have mapped things to the complex plane, then we can make more active use of the rich toolbox of complex analysis. So we will see how the Cauchy theorem will help us, and also the homotopy invariance of complex contour integrals over meromorphic functions. So we are slowly starting to make use of all the goodies in complex analysis. All right, let's try to fulfill this mouthful of promises. What were the latest coordinates I showed for the string worldsheet? Well, we Wick rotated proper time tau to Euclidean time t, and then we were combining spatial and time-like coordinate to these complex numbers. So this was what happened before the break. But we saw that we are now in a conformal field theory thanks to residual gauge invariance. So we are free to do our favorite meromorphic transformations with that. And a particularly nice one is the exponential map, which does us all the favors that I just outlined. And needless to say, the exponential map is part of that club of meromorphic transformations. Okay, so what is that exponential map concretely doing as to cylinders and planes? So after exponential map, the new coordinate will depend on tau and sigma as shown here. And I hope I find enough colors to draw everything neatly. What I meant by cylinder is the same picture that you saw in the introductory part of yesterday, that closed string worldsheets have topology of a cylinder. So let's look at snapshots of the closed string at different times. And needless to say, time keeps on flowing, even when we have stopped taking snapshots. And this is the situation before exponential map, where sigma runs periodically here over the circle from 0 to 2 pi, and then plugging that into that exponential map zeta. What happens? Okay, I guess in your complex analysis lecture you already spent some time looking at the image of the exponential map. So what these snapshots of the closed string are getting mapped to, so the top and bottom of the cylinder, so to say, gets mapped into concentric circles. And okay, maybe this is an artifact of how I drew it. I just singled out 2 points on the closed string where I drew the vertical line. So these vertical lines get mapped over here and there, just to give you a feel of how they align. And these points where I went into dashed lines, let's also draw dashed lines over here in the image under the exponential map. And this is important to give you a feel for where infinite past and infinite future goes. So to be more precise, it's the dashed lines down here. I mean, this I would say is infinite past. And infinite past is now getting mapped to, well, this environment of the origin. Whereas infinite future, the dashed lines up there, they are now outside that outer circle. So this, if I take the upper cutoff to infinity, will map to the point at infinity of the Riemann sphere. Okay, so what I was just saying in words, the fate of the 2 types of infinities on the complex plane is as follows. Infinite past goes to the origin. This is maybe the more digestible part, and well, pretty clear by inspection. Imagine you have an exponential and then you send the real part of the exponent to minus infinity. Clearly, this suppresses everything to 0, no matter what the phase is. Oops. And then infinite future. Well, there, to see that the phase doesn't matter at infinite future, you may again need to use the inverse map, sending zeta to 1 over zeta to make this more precise. But if you're ready to trust me, infinite future will also map to just 1 point if you work on the Riemann sphere. I mean, one often uses stereographic projection, where the origin is, say, the south pole, and the point at infinity is the north pole of a sphere. So, yeah, it's just a point. Yeah, and as I was promising, one of the many benefits is that the periodicity in sigma becomes automatic. I mean, the spatial coordinate of the closed string worldsheet is now the phase, and obviously going from sigma to sigma plus 2 pi, we'll just do, rotation by e to the 2 pi I. Okay, so this is a very convenient choice of coordinate for multiple reasons. Let's say one of the reasons is that we can make more contact with the Cauchy theorem. This is where I want to get to in the next minutes. And on the way there, let me make sure that you have seen the mode expansion in all the possible coordinates. So the mode expansion of the free boson, we looked at it yesterday in light cone coordinates, where we saw that the sigma plus derivative, say of the left mover, had the following form. Up to some not so relevant normalization factors. There were Fourier modes, alpha and mu, and here plane waves in sigma plus. It's a discrete Fourier expansion because of the periodicity. I can't afford a continuous analog of the variable n. So this is the formula you saw yesterday. And now we are doing this chain of little tweaks. So there was this transition to complex coordinates. And then there is barely any change to the mode expansion, except for maybe this prefactor minus I, but this is not the point I want to stress. This I'm just writing for completeness. What is a little bit more interesting is how it looks like when we are transitioning to the plane. So it's a chain rule that we need to translate the z derivative into a zeta derivative. Remember, zeta being the exponential of z. So as you all know, I mean, how to differentiate the exponential, there is this zeta factor over here. And now, what used to be a Fourier expansion is now a Laurent expansion. So now the coefficient of the Fourier coefficient alpha becomes essentially an integer power of zeta. And okay, given that it's e to the minus nz upstairs, we have a minus 1. And given that we have this Jacobian here, and converting the del z into a del zeta, it's in fact an exponent minus n minus 1. Okay, and in all of the three equations I have been lazy. Maybe I should tell you for completeness how the other half can be recovered. So by other half, I mean the right moving friend with sigma minus in the place of sigma plus, where the Fourier coefficients had the name alpha twiddle. Then here, the other side is send z to z bar, and again, alpha to alpha twiddle. And here in the zeta coordinates, it's of course the same. If I do exponential map, then z goes to zeta and z bar goes to zeta bar. Okay, so looking back, one may have asked why not to call the alpha twiddle alpha bar instead. But yeah, what I wanted to say is what used to be an undebated Fourier expansion became, going here, all of a sudden a Laurent expansion. And well, when you did Fourier analysis, there is always a point where you want to pick up a specific Fourier mode. So you just integrate against the test function, against the plane wave, to extract a particular mode. How do we do that for Laurent expansions? How do we extract a particular mode in this infinite sum over n? What's the analog for integrate against a suitable test function? So for Laurent series, this is about contour integrals. If you want to extract a single alpha from that infinite series, what you need to do is, well, it's in a certain sense the image of the Fourier integral of this, these changes of variables. What you need to do is do a contour integral of the complete series here, namely the del zeta. And to make sure you are catching the right alpha, please put in a factor zeta to the n. So here I'm giving you the contour integral representation of the individual modes. And yeah, to be on the safe side, let me just call them Fourier/Laurent modes. Then you can choose which viewpoint you like more. Okay, so what is going on here? First of all, the notation here and elsewhere will be that whenever I write BR of Z, I mean a circle of radius in the subscript, and the center of the circle is in parentheses. So in general, this could be around Z, and here it's around the origin. And the reason why this identity holds true is Cauchy. Namely, I refer to the contour integral of an integer power of that integration variable. This is a contour around the origin. And it's usually 0. I mean, you would, for positive n, you say it's a holomorphic function. Closed contour integrals are 0 and basta. But if we have negative powers, we need to be more careful. And it's the simple pole which gives a non-vanishing contour integral. So it's the case m equal -1, which gives you a non-vanishing contribution. And in fact, that contribution is independent on the radius. Yeah, maybe you were a bit surprised, why didn't I specify the radius? I mean, the left-hand side doesn't depend on r. And this Cauchy formula doesn't care about which radius of that circle you pick. Okay, so this is a key mechanism which will evaluate for us various contour integrals, which will collapse for us various Laurent series. So please internalize that one. And this is just the first example out of many others of contour integral representations. We can do something similar for the conserved charges associated to the Noether currents over there. I'm pretty proud that I managed to leave this formula alive for the J's associated with meromorphic eta and the J bar associated with the anti-meromorphic eta. So this is so far the conserved Noether current. And one typically converts Noether currents into the associated charges, which are conserved in time. And this conversion requires me to do a spatial integral over a constant time slice. And also the constant time slice will be a contour integral. In order to represent the conserved charges. Namely, the constant time slice. Let's think about the cylinder, which maybe I should have not erased. The constant time slice on the worldsheet is fix t and just have sigma pass through all these values. And this is before the exponential map. Now, after exponential map, this is the phase. So you keep the radius fixed, given by the time. And yeah, you just exhaust the entire circle in the zeta plane as you scan over all these values. So the upshot is that a constant time slice in the zeta coordinate, namely on the plane, is just a circle whose radius is exponentially related to time. So now the conserved charges associated with conformal transformations. Well, the conserved charge associated with the Noether current is time independent. But time is now radius in the zeta coordinate on the plane. So whatever I'm writing down is independent on r, because the charge is conserved. And let me introduce this notation here. Q for the conserved charge. It's an integral over a constant time slice, identified as a circle. And what I'm integrating is this J of eta over there, the product of the energy momentum tensor and the meromorphic map eta. Okay, as you see, my zetas are not getting more beautiful as I write many of them, so I will stop with the zetas and rename zeta to C henceforth. So from now on, we will do virtually everything on the plane, unless stated otherwise. So if you see a Z henceforth, assume its coordinate on the plane. Yes, please.
Probably just the minor detail, but why is sigma in the open interval 0 to pi? I mean, like, shouldn't one of the two endpoints be included? What happens if I mean, both endpoints are excluded?
Both endpoints. You mean you would have preferred minus pi to plus pi?
No, I know. I was wondering if, like, 0 should be included in the interval or not.
Oh, sorry, the endpoint. Oh, I see, I see. Not sure. To be on the safe side, maybe excluded. I mean, later when we do moduli space integrals, we typically take this compactification. I'm not sure whether the endpoint is part of it or whether I'm taking these round brackets serious or not. That's a good one.
One of the two should be square.
I'm not sure.
If you don't have range cards on the complex plane, then it doesn't matter. Just make it
Oh.
other. But 0 to pi are really identified, like you're not on different sheets.
Yeah, but like this, that could be a branch cut.
Yes.
Yeah.
And you have to say either 0 or pi. Not one.
Yeah. But yeah, typically this is a set of measure 0 in the calculations I'll do. This is the reason that I'm hesitating to give a definite answer. Yeah, so there is this Cauchy theorem in action, and the other essential tool from complex analysis that I will borrow is homotopy invariance that are already mentioned in words and which I should really write down as a precise equation. So what will drive most of the discussions in the rest of today's lecture is the following. So imagine you have to perform a contour integral in the complex plane. So here, real part, imaginary part. And the plan is to integrate from one point z1 to another one, z2. And the question is, what does the integral actually depend on? Say I prescribe a path gamma 1, and suppose that f is meromorphic. Then, as a very nice property of meromorphic functions, the integral is actually just a function of the endpoints, not of the path. Which is to say, you can choose any path you wish to get from z1 to z2, as long as you stay away from singularities. So imagine you have these two options, gamma 1 or gamma 2. And as long as the function is meromorphic and we are not crossing any poles, these two contour integrals will be the same. So the assumption is that f is in fact holomorphic in here. So this is known as homotopy invariance of meromorphic functions, or I should say the contour integrals thereof. And yeah, the essential prerequisite is meromorphicity. And since everything is meromorphic in here, you can already see that this is a hot candidate to apply that homotopy invariance to. Okay, so just to write out that condition more clearly. So yeah, we want meromorphicity, no z-bar dependence whatsoever, and we don't want to see any poles in the interior. So that closed contour here should not enclose poles. Okay, so this is the second central piece of complex analysis aside from Cauchy. Yeah, so now as a next step, I want to generalize our observation we just made for the free boson. We tracked this z derivative of x under conformal transformation, and we saw that it picked up a factor of zeta under the exponential map. So this fun fact I want to generalize to give the definition of a conformal primary field. And those, in turn, will be the gateway to develop the notion of operator product expansion. That's probably the thing I want to finish before going into the break. Yeah, but one thing at a time. So as I was saying, generalize the transformation law of del x. Well, we saw if you pass from z to some meromorphic function of it, then you pick up a factor of Jacobian, which in that case of exponential map was just a factor of zeta. So picking up this factor of zeta, you can say schematically that this transforms like a vector. But take it with quotation marks. This is just an analogy for the beginning. And whenever you have been shown a vector, you can ask, what's the corresponding tensor? What if my Jacobian appears not only once, but multiple times, like many indices to be transformed in the same way? So what my goal is to introduce some sort of tensorial uplift of this transformation law. So the generalization goes to arbitrary powers of that Jacobian, which enters here through the chain rule. So I'm looking at the specific Jacobian that converts partial z into partial zeta. And by admitting a more general power of that Jacobian, this leads us to the notion of, a kind of tensor. But I won't be using these loose terms, vector and tensor here, but instead, the definition is for so-called conformal primary field. So an object, phi, is called a conformal primary if it transforms in the following way. So it's similar to defining a tensor for you, a tensor in GR by its transformation law. And here the defining transformation law for a conformal primary field is that in passing from z bar to zeta and zeta bar, I want that my transformed field looks as follows. So prime saying this is the transformed field, and I now want to admit an arbitrary power of that Jacobian. And separately, some power h for the Jacobian in the meromorphic variables, and yet another Jacobian to a separate power h bar for the antimeromorphic counterparts. Okay, so the definition incorporates some numbers h and h bar, and these numbers are called the weight or the conformal weight. Maybe I'll be lazy sometimes and skip the word conformal, but whenever I will say weight henceforth, then I mean this pair of numbers that tracks the powers of these Jacobians. But most importantly, this is still within the cosmos of conformal field theory. I only impose this for meromorphic and anti-meromorphic zeta, aka for conformal transformations. So we speak of a conformal primary if such conformal transformations have the effect spelled out here. Oops. Okay, that's the definition. And yeah, as I said, the simplest non-trivial example, or the motivating example, is that of the free boson. So the Z derivative, well, you saw it happening in front of your eyes. There was one power of the meromorphic Jacobian and no power of the anti-meromorphic one. So here the pair of H bar is 1, 0. And similarly, if I had played the same game with a Z bar derivative, then one would diagnose the opposite configuration, 0, 1 for H and H bar. And indeed, the analogy to tensors is quite useful to get more intuition. It's a little bit like a contravariant tensor, contravariant meaning downstairs indices. But it's a bit funny in the sense that some indices are meromorphic, namely the first H of them, but the others are anti-meromorphic. So it's a bit like distinguishing two species of indices, and that's admittedly different from the GR analog of tensors. So it's of partial use to get some first intuition, but not to be taken literally. So yeah, conformal primaries transform somewhat like tensors with H plus H bar indices, but with a little caveat that the two sorts of indices need to be kept apart. Okay, that's a definition which admittedly may sound a little bit weird and technical first time you see it, but it will be really important throughout the course to track the properties of various worldsheet fields. I mean, we will, in the superstring case, meet additional conformal primaries of weight 1/2 or 1/16, and it's really good and useful to discuss their properties once and for all. So my apologies if this at the moment sounds a little bit like an overkill, but it will definitely pay off, both for understanding future ingredients of the superstring worldsheet, but also to connect even more with the complex analysis machinery. Okay, here I was talking about a finite conformal transformation. The zeta can, for instance, be the exponential map. No need to be close to the identity. So let me now give the infinitesimal version. How does the general formula here specialize if zeta is close to identity? So this once more means that we only work to first order in Ada. And we furthermore make our life simple. Let's keep the Z bar untouched, just to save us from all the writing work of the Z bar business. Okay, so I want to now study the infinitesimal variation, comparing the transformed phi prime to the untransformed one. So here this Ada variation is defined to be phi prime minus the unprimed one. And now there are two effects coming together. Oh, sorry, unprimed. When I say unprimed, I should write unprimed. There are now two effects coming together. We would like to use the formula over there for phi prime. We want to get rid of the prime. But I can only do that if the argument is zeta, the new one. But here, the argument is z, so I can't use the formula yet. I need to compare z with zeta. So you need to plug in this into the argument, and at vanishing eta, I could use the formula. But since the argument has this shift by eta, I need a Taylor expansion. So I do get a displacement term that tracks that z is different from zeta. So this displacement term is here. And okay, if it wasn't for infinitesimal eta, I would have an infinite Taylor series following up. But the good thing, since eta is taken to be infinitesimal, I just swallow everything beyond the first correction, the Taylor series. Okay, so this takes care of the z versus zeta issue. But now we also need to take care of the Jacobians. So we are comparing a term which will catch some Jacobians after using the formula with another term that I just subtract, which of course doesn't have Jacobians. So here is a second contribution to the infinitesimal transformation, namely here a Jacobian minus 1. So this is maybe the more obvious term. Or to my personal taste, the first one is harder to see than the second one. Okay, and here I try to be excruciatingly honest about what the argument is. I mean, we were going from z to zeta, but in fact, if we drop everything eta square and higher order, it doesn't even matter whether I put a prime here or not, whether I put a zeta here or a z. So the simplest way of talking about the first order in eta terms is as follows. And okay, also here you plug in that zeta is essentially z plus eta and extract the first order term. So this is rather mechanical, and you will get the derivative of eta, hopping out from the Jacobians. Okay, so this is where the definition of conformal primaries takes us if we take the conformal transformation to be an infinitesimal one. So once more, all of this modulo eta square. Yeah, this is what conformal transformation is supposed to do. And now let me try to make a connection with all the Noether current discussion from before the break. When we assume we are in a conformal field theory, we are here spelling out a specific form of a conformal transformation. And in any quantum field theory, you want that such symmetry transformations are generated from the charge. So this is a general QFT wisdom, even not tied to conformal symmetry. In any QFT which has symmetries, you want that the symmetry transformation must be generated by the commutator with the associated conserved charge. Maybe some people call this the quantum version of the Noether theorem. I'm not exactly sure whether this is a universal terminology or whether it was specific to my lecturers back then. But yeah, it's meant to be a very general statement applicable to any QFT with symmetries, that symmetry transformations must arise from commutator with a conserved charge. Now, this should in particular hold here. We have a conformal field theory, and we have an eta variation with this very explicit form for conformal primaries. So here we must demand that the above transformation law of conformal primaries, that they come from a commutator with conserved charge. And let's save the expression for the conserved charge. I'm sure I'm erasing the other board earlier than I should, so let me save that expression here. The conserved charge associated with this infinitesimal conformal transformation eta is given by a contour integral. As I apologized already, my zetas become z because they are easier to write, and it's just an integration variable. You can call it any way you like. Yeah, so in order for global consistency with everything we know and love about QFT, that one has to hop out from a commutator with this contour integral. And admittedly, at first hearing, this sounds pretty hard to believe. But in fact, there is a way to tie these two ends together, and that goes through the notion of operator product expansion. Okay, so I'm now sketching the formalism, or I tell the story behind how you can make this match with that. Yeah, perhaps the first move is to get rid of the commutator. I mean, so far we didn't really talk much about ordering. I explicitly refused to treat the alpha oscillators as operator valued before, so you may already find it a bit weird to have a non-vanishing commutator around. So how can we make sense of that commutator in the context of what I've been telling you so far? So in which way do I want to see the commutator evaluated? And here I want to appeal to the notion of time ordering. I mean, in interacting quantum field theories, you were probably exposed to the notion of time ordering, for instance, in solving the time-dependent Schrödinger equation. If you have a linear differential equation, tau derivative of psi is Hamiltonian h times psi, then you solve this by an exponential. But in general, Hamiltonian is time-dependent. So you don't have a pure exponential, but a time-ordered exponential, like an infinite series of iterated integrals. So in that way, time ordering appeared pretty natural in your QFT course, maybe already in your quantum mechanics course. So in one way or another, I assume all of you have seen time ordering once in your life before. And this we want to import here to the worldsheet. Impose time ordering, and in the first place, time ordering is imposed on the cylinder. And it was in the cylinder chart where we spoke of proper time in the first place. But now the cylinder is out and the complex plane is the place to be. So what used to be time ordering is now radial ordering on the plane. So commutators are evaluated in the sense of radial ordering. So for this specific commutator on the plate, I want to associate the plus term with the radial ordering where z has a larger absolute value than w. And this is just realizing the QFT mantra that later times should appear on the left. I mean, this goes all the way back to how you write the Schrödinger equation, that the Hamiltonian is left acting on the wave function. So solving the time-dependent Schrödinger equation gives you path-ordered exponential where the latest time appears leftmost. And late times translate into large radii. Remember, infinite past is the origin, so time flows radially on the complex plane. Okay. This is how the first contribution to the commutator is made sense of. And now there is this minus term in the commutator where phi is placed left of t eta. And being placed left means that we need to invert this inequality among the radii. So in both terms, we realize the invariant statement later times on the left, please, or larger radii. Okay, this is how the commutator is to be understood. And that commutator appears inside a contour integral. So how can we make this radial ordering play out with contour integrals? We have inequalities among the radii, and contour integrals have a radius to play with. Okay, this looks like fitting well together. So the commutator on the table is Q, which has a baked-in contour integration. And now it gives two separate contour integrals, one for the plus term and one for the minus term. So in both of these individual contour integrals, I must make sure that the respective inequalities are respected for the radii. So there is one contour integral with z having the larger radius and the other one vice versa. Yeah, and the integrand is the same, and well, I no longer need to track the order. I mean, we have already been careful about the order of the operators to determine the radii. So therefore, I will just ignore in which order the operators are written. So the ordering information is now placed into the integration contour and doesn't need to be tracked separately in the integrand. It would be overkill.
Sorry, and why is the time ordering defined with a minus sign?
Oh, you mean why it's not flipped, or?
Yeah, no, I mean, why is that a minus sign?
Okay, just imagine it's a non-commutative variable in the commutator. Then the bracket of A with B is AB minus BA. So it's the minus in front of BA, which I've just transferred here. So yeah, as I said, ordering info is already in integration contour. It seems like I'm quite lucky that most of the relevant pieces of information are still visible on one board or another. Yeah, let's now simplify this symphony of contours a little bit more. So what we have is a difference of two contours which have certain commonalities. So the plus term has the point W fixed somewhere, and then the integral over z is over a sufficiently large radius. So this is a way of satisfying the inequality that absolute value of z has to be larger than absolute value of w. So this is in the plus term. And then the minus term has a similar integration circle, but now the radius for the integration circle is smaller than the absolute value of w. So we have to deal with the difference of that. And here we can take advantage of the holomorphicity of everything in the integrand. Well, in the first place it's meromorphic, but in fact, as long as I keep z away from w, it's in fact holomorphic. Or putting it differently, there is a contour deformation that we can do, which does not cross the critical point z equal w. By doing a contour deformation, we can map that difference into a single integration contour. So once more, W is sitting rigidly somewhere in the complex plane. And okay, there was with a plus sign a piece of contour for Z that passes like this. This was there with a plus sign. And then with a minus sign, Z is moved along here. So minus sign means I reverse the orientation. So by puzzling the contributions from here and there together, and by doing a contour deformation, I can, I can map all of this to just a circle. Integrate Z along a circle, but now centered at W rather than the origin. So what this means, the difference of the two contour integrals on the other board become a single contour integral, which is claimed to catch the commutator. So now it's in the agreed upon notation, B, R at W. And okay, well, the radius of that circle is in that case not relevant, but if there were other fields at other points, make sure the radius is small enough. So whenever in doubt, take the smallest radius that still encircles what you want to encircle. Good, this is a slightly more tractable expression for the commutator. And what have we achieved? Well, the original plan was that we want to argue this commutator reproduces the infinitesimal conformal transformation. Okay, how can we implement this rather tall order? We want to impose that this contour integral reproduces the infinitesimal transformation of a primary field. It should better reproduce the above expression with a minus sign, but that's not so important. So how can this be? And well, you can already smell if there is a contour integral that should eventually disappear in favor of an unintegrated expression, you can probably smell that this will involve the Cauchy trick in one way or another. So we want to use Cauchy in the following form. Let's adapt it to the integration contour at hand. We integrate Z in a circle around W. And the best way of massaging the integrand is to organize it in powers of Z minus W. And well, such contour integrals, as I stated before, are usually zero unless you're dealing with a simple pole. That's why I'm writing a Kronecker delta here, enforcing the exponent m to be minus 1. Okay, so the plan is to use Cauchy to get from here to there. And now the big question is how to make that happen. How to translate this operator product to certain Laurent powers in Z minus W. So let's just dream wild. What do we need to do to make that miracle happen? So for instance, if the goal is to produce this term here in the target expression for delta eta, this we get if we take the liberty to set, if you set this product of t and phi into the first time you see it, I'm sure that the right-hand side looks like drawn out of thin air for you. Here, all I'm doing is wishful thinking. What do I have to put into the integrand in order to get out what I should get out? This is part of the target expression. And if I violently cook up a term in the integrand, which makes that happen, then, well, I have an undifferentiated eta. So if I want an undifferentiated eta to be isolated, then t and phi should better conspire to give a simple pole. And the residue of that pole should be derivative of phi, because this is what I'm expecting from the infinitesimal transformation law. And let's apply the same wishful thinking to the other term in the target expression. I mean, this infinitesimal variation also has a term proportional to the conformal weight h, and it has a differentiated eta. So differentiated eta means that somewhere in behind the scenes there was a Taylor expansion going on. So it's about the first order in the Taylor expansion, but it should still be from a double pole in overall. So this means that it must be embedded in a simple pole. So in order to make that happen, the operator product should also have a double pole with residue h times the undifferentiated. Okay, so this finishes the diagnosis. What kind of rules do we have to invent to ensure that this commutator indeed gives you the conformal transformation as ordered by QFT general wisdom? Yeah, so to wrap up, I will write down the wishful thinking expression. And then we are probably all ready for a break. So, in summary, we need to impose that there is a singularity structure between T and an arbitrary conformal primary field of weight h. I mean, remember, the only thing I've ever told you or imposed about phi is that it's a conformal primary field, like this kind of tensor with respect to conformal transformation. So when those two come together, there must be a double pole with residue proportional to the primary field itself. This gives the term with a differentiated eta in the conformal transformation. And I furthermore want to see a simple pole. And there the residue is the derivative of that primary field without factor of h. And then, apart from that, I have no clue what comes next. I have no clue about the regular powers in z minus w, because regular powers will never ever be seen by that contour integral. So from the analysis on the board, I fear I cannot tell you anything here. The only thing where we do have information is the singular terms, and in particular, there can't be a triple pole, quadruple pole, and so on, because if it was there, we would see higher and higher derivatives of eta. Don't be worried, this has nothing to do with the linearization in eta. I mean, we are still consistent with an infinitesimal eta if we admit higher derivatives in W. And all of them are absent, hence no higher order pole than that. Okay, so these arguments lead to writing down an operator product expansion like that. Yeah, time for the break.